All right. Um, Hello, class. Good morning. I apologize for this lesson being a little bit earlier than usual. We had a staff meeting via Zoom this morning, and I decided that I was gonna just wake up early and went for a run before the meeting and got everything done a little bit early. So that was nice. Um, it's funny because before the Zoom meetings, they always tell the staff, because we have a lot of staff who are clueless with technology, and so they say, mute your microphone if you're, eating something or whatever. And I know about the technology, so I kind of like before every meeting, I've been turning on my camera and my microphone and doing something really obnoxious, but pretending like I don't know what I'm doing. So uh, for the previous meeting, what I did was I ate a banana really obnoxiously. So I was like with the banana, and then this morning I was gargling mouthwash, like right into my microphone. So if anyone had their mic, anyone who was listening to the meeting, all they heard was like, so it was funny. I got to keep myself amused somehow. A couple of news announcements. Go ahead and turn in the homework and the quiz at your earliest convenience. Next week, so these are problems from the workbook. Next week, I'll be actually doing free response questions from past AP Physics 1 exams. We'll only have class Monday, Tuesday, Wednesday. And on Wednesday, I'll invite you to join the Discord session. So any last minute questions about the AP exam, we can try to answer those for you. And also my AP Physics C class will have their AP exam on Monday. And so I'll be able to kind of hear from them what it was like, and so I can pass that information on to you. I posted a list of the topics on the Discord, and I also posted some College Board resources on the Discord, so please go check that out if you're taking the AP exam. Thursday and Friday, we're going to have no class, so we'll just kind of take those 2 days off, and then after that, so a week from Monday, we'll start in with astrophysics, which was far and away the topic that you guys are most interested in, it sounds like. So hello, everyone. Hey, Sebastian. Hey, Theo. Hey, Elena. Hey, Will. Hey, Matthew. And hey, Vicky. Hey, Matthew, did you watch the last episode of Clone Wars, and was it good? I'm curious. All right, so let's get right into it. I'm going to do the problems that I meant to do yesterday. So yesterday I meant to do pages 199 to 204. So I'm on page 199 right now, and let's read it. It says a box of mass M is tied to a rope that is wrapped around a pulley. The pulley is initially rotating counterclockwise and is pulling the box up. The box slows down and stops instantaneously and then moves back downward. The dot below represents the box. Draw a free body diagram showing and labeling any forces acting on the box initially. Draw the relative lengths of all vectors to reflect the relative magnitudes of all the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So you guys have seen this free body diagram many times by now. And the free body diagram has two forces on it. It has a tension going up, and it has a weight force going down. Now, I am drawing the tension as actually, it says the box is slowing down, doesn't it? So that means that gravity has to be bigger than the tension. Okay, otherwise the box would be speeding up. Part 2 says on the diagram at right, draw and label the forces that are exerted on the pulley as it initially rotates. Clearly indicate at which point on the wheel each force is exerted. So the wheel, here's the wheel, it's going to have a sort of a normal force going upward. And that normal force comes from the support. See how the wheel is being supported, it's attached to the ceiling. So there's got to be an upward force. There's going to be the tension force. Tension is the same throughout the rope. So there's going to be a tension force that's pulling down right here. And I would want to make that the same length as this one. So made them the same length. And it's acting along the edge. And then we have a downward force, which is the weight force from the weight of the pulley itself. So because the pulley isn't moving, the net force has to be 0 on the pulley. So if I look at these two arrows, the two downward arrows, they're actually longer than the upward arrow. So I'd better make my upward arrow the same length as my downward arrows. So this is a more accurate free body diagram. Something like this. Okay. What force is responsible for the net torque on the pulley arrow is the tension. Let me see if anyone checked in and said hello. So looks like Clone Wars was amazing. It's on my watch list, the Clone Wars. Maybe I'll lower velocity as a function of time from the initial instant until the weight comes back down to the same height. Take counterclockwise as positive. So we can see that the wheel starts out spinning counterclockwise. It slows to a stop, and then it starts going the other direction. So we have a clockwise or a counterclockwise rotation, which is a positive angular velocity, and then a negative one. So we're going to have, basically this is going to look like a straight line that slopes down. Okay? And I don't know how many bars up, but the area under the curve, so this positive area should equal this negative area because the weight came back down to the same height, which means that it had a total displacement of 0. So we want the area under the velocity time graph to be 0. Angular acceleration is the slope of the velocity time graph. So this is a constant negative slope, so I would just draw a constant negative value for the angular acceleration. All right. Next scenario. A meter stick is set on the edge of a table so that all but a negligible bit of its length is off the edge of the table as shown. The meter stick is released from rest horizontally. The meter stick's mass is m and its length is L. The rotational inertia of the meter stick around its end is 1/3 ml squared. Sketch a force diagram for the meter stick just after it has been released, meaning that it's still horizontal, but there is no longer anyone supporting the right end of the meter stick. So basically there's going to be an upward normal force from the table, and there's going to be a downward weight force. Okay. The weight force acts from the center of mass. The normal force acts from the point of contact. I drew the downward force as bigger than the upward force because the meter stick is going to swing down, right? Identify the point on the meter stick around which the meter stick is pivoting. Mark this point with an X. So this is the pivot point right here, the left end of the meter stick. Is there more than one choice for the pivot point? What are the implications? You could use more than one pivot point. That's going to change which forces have R equals 0 and which ones don't have R equals 0. So I would say, well, I would say torque equals F perp times R. Moving the pivot point changes the R values. Okay. Determine the net torque about the meter stick's left end instantaneously after being released. So, as I said, torque is F perp times R. And the force that is providing this torque is gravity. Okay, so what does it say is does it give the mass of the meter stick? I don't think it does give the mass of the meter stick. Oh, it says the meter stick's mass is M. So the perpendicular force is the weight force, which would be mg. And the weight force acts from the center of mass, which is halfway to the end of the meter stick. So the meter stick's length is L. So halfway would be L over 2. Like that. So I would say it's mgL over 2 is the net torque. The normal force does not provide a torque because it's acting at the pivot point. So it has R equals 0. Starting with Newton's second law, and in rotational form, derive an expression for the initial angular acceleration. All right, can do. So the rotational form of Newton's second law says that net torque equals I times alpha. I'm not sure how to make an alpha. We'll just say that that's alpha. The net torque we just saw was mgL over 2. The I value, which we saw, was 1/3 ml squared. It's right here. That's the inertia. Okay, so I will use that on the right-hand side of the equation. So we have 1/3 ml squared times alpha. So we can see that the masses cancel out. We get GL over 2 equals L squared alpha over 3. Then we can cancel out a factor of L. So we have G over 2 equals L times alpha over 3. And multiply both sides by 3, divide both sides by L. We get 3/2 G over L equals alpha. All right. So that wasn't too bad. Derive an expression for the linear acceleration of the far end of the meter stick in terms of G. What is the consequence of your answer? Explain in terms of what would happen to a penny placed on the end of the rod before it's released. Okay. So we know that omega is V over V time, or sorry, V equals omega times R. That's for something that's rotating. This relates angular velocity to linear velocity. And so we know that so basically dividing by time again, whoops, what did I do? So we have V equals omega R. If we divide both sides by time, we get V over T equals omega over T times R. All right. V over T is linear acceleration. Omega over T is angular acceleration. So we have this relationship between linear acceleration and angular acceleration. We already calculated that the angular acceleration is 3/2 times G over L. Now the question is, what is the R value of the end of the meter stick? The R value of the end of the meter stick is the entire length of the meter stick. Okay? So the entire length of the meter stick, so R is actually L. So we can see that the L's cancel out because we have 1 over L times L, and we get that the linear acceleration is 3/2 G, which is greater than G. Okay? So that means that the right end of the meter stick is going to accelerate downward faster than gravity. If you have a penny, the penny is just free falling, so it accelerates downward at gravity. So what would happen is that the meter stick would go downward faster than the penny would, and the penny would just be falling through the air. Doesn't stay with the meter stick. Okay? It's kind of neat. You can try it out yourself. A ladder is set against a wall so that the ladder makes a 30-degree angle to the floor. So that means that this angle right here is 30 degrees. The wall is very smooth. Very smooth means no friction, but the floor is not. The ladder only remains motionless as long as a person holds it in place. When the person lets go, the ladder accelerates downward and to the right. Blake analyzes this scenario and identifies that the 4 forces acting on the ladder are its weight. That's correct. The weight goes down right there. The normal force from the wall. The normal force from the wall acts outward like that, away from the wall. The normal force from the floor, which acts upward from the floor. And the friction between the ladder and the floor. So we can see that the end of, the bottom of the ladder is going to want to slide out, and so what that means is that the frictional force is going to be inward. So that's where all the forces are acting from. He correctly ranks the magnitudes of these forces as gravity is the greatest, normal force from the floor is next, weight force is next, and friction is last. Draw and label the forces that are acting on the ladder. just did that. Explain why the force of gravity has to be bigger than the normal force. Okay, so basically, the reason that that has to be true is that the ladder is falling downward. Okay, it's falling down. The center of mass of the ladder, which is in the middle, is going downward. Okay. So what I would say is something like the center of mass of the ladder accelerates downward. This means that the net force in the y direction has to be less than 0. The net force in the y direction, see, there are only two forces in the y direction. There's the normal force and the weight force. So this means that mg had better be greater than the normal force. Okay. Explain why the normal force is greater than the normal force from the floor is greater than the frictional force from the floor. Equations may be part of your answer, but equations alone are insufficient. Okay. So what I would say is that the force of friction is equal to the coefficient of kinetic friction times the normal force. Okay? And the coefficient of friction is less than 1. So that means that the frictional force has to be less than the normal force. Okay? Yeah. Okay. Explain why the normal force from the wall is greater than the normal force from the floor. All right, we can do that. So this comes from, if we look at the ladder is, as the ladder goes flat, the end of the ladder, the bottom end of the ladder slides out. So that means that the center of mass of the ladder is actually accelerating rightward. Okay? So as the ladder rotates, its center of mass accelerates rightward. This means that the net force in the x direction has to be greater than 0. Now, what are the forces in the x direction? There's only two of them. There's friction, which goes to the left, and there's normal force from the wall, which goes to the right. So that means that normal force from the wall minus friction from the floor has to be greater than 0. This means normal force from the wall is greater than friction. Okay? Blake states that the ranking could not be completely determined until it was demonstrated that normal force from the floor is greater than normal force of weight plus the force of friction. Um, all right. Explain how this expression is demonstrated by the scenario. So notice how the force of friction is the force of friction is the force of friction is going to the left. The normal force from the wall is going to the right, and the normal force from the floor is going up. These four forces are providing the torque. Okay. And the torque has to be positive because the ladder is going to rotate counterclockwise. So that's where this is going to come from. So basically, the net torque has to be greater than 0. Okay? And the torque, I'm calculating the torque about the center of mass. All right? And so if we were to calculate, so I guess I can work it out. We want the perpendicular component of all of these forces, okay? All of these forces act at a length of L over 2. So the R value is length of the ladder over 2. Let's see. So now I need to draw some lines here. So there's that line. That would be the perpendicular component of the wall's force. This line would be the perpendicular component of the normal force from the floor, and this line would be the this line would be the perpendicular component of the what am I trying to say? Perpendicular component of the force of friction. So if I actually calculate what the net torque is, okay, if I actually calculate what the net torque is, this one's kind of tricky actually. We've got normal force from the wall times cosine of 30, because this angle right here would be 30 degrees. Oh no, wait, that angle would be 60 degrees. My bad. So cosine of 60 degrees. So we have normal force from the wall times cosine of 60 times L over 2. That's the torque from the wall. Then we have the floor. This angle is 30 degrees. Okay. So that gives a torque of normal force from the floor times cosine of 30 degrees times L over 2. And then lastly, we have the force from the floor, which is also acting at 30 degrees. So that's going to be force from the floor, or frictional force from the floor, times cosine of 30 times L over 2. So which of these torques is positive and which is negative? We've got a positive torque from the normal force from the floor, and the other two are negative. So we have this one's negative, this one is positive, this one is negative. So that's an expression for the net torque, and it has to be greater than 0. All right, and so the L over 2's all cancel out. All right. Then if I add over both sides, I've got n sub f cosine of 30 is greater than nw cosine of 60 plus the force of friction cosine of 30. I kind of think I might have goofed. I think this might have been, this is supposed to be 30 so that they all cancel out. I think that's what I forgot to do. I'm going to just double check if I look at this graph here. This is 30, this is 60. Yeah. So if we cancel out the cosine of 30, we get n sub f is greater than n sub w plus force of friction. So that one was kind of tricky. But, you know, it is what it is. We just got to calculate the torques. All right. Well, thank you for watching, class. Remember, submit the homework today. You can submit the quiz today as well. It's just the daily items from last week. Next week, we'll be doing free response questions. And then Thursday and Friday of next week, we won't have class. So start thinking of questions about the AP exam if you have them, and I'll answer them on the Discord on Wednesday. Have a great rest of the day. Have a nice lunch, and I'll talk to you on Monday. Bye now.